All right, in this problem we have a collision between a ball putty of mass 200 grams, which is moving at a speed of 7 meters per second, and it comes in and hits and sticks to a block of mass 500 grams that is initially at rest on a frictionless table. The block is attached by a spring with a spring constant of 75 newtons per meter to an immovable wall. After the collision, the block and the attached putty undergo simple harmonic motion. So there's a few questions regarding this situation. So the first one is, what is the speed of the block putty right after the collision? So the problem is actually helping you a little by giving you a picture of what things look like right after the collision. So if you look at the top right, you see that the collision is supposed to have taken a very, very short amount of time, order of milliseconds. So after the collision is done, the block and the ball are moving together with some velocity, and this question is about finding how much is that velocity. At this time, the spring hasn't had time to compress. The block hasn't moved any appreciable distance. The collision happened very quickly, and the block has a velocity, the block putty has a velocity v. So we're looking for that velocity. Very important to notice, every time you look at a problem and the statement mentions a collision, you're immediately going to think about the fact that all collisions conserve momentum. All collisions conserve momentum. As long as you apply the conservation of momentum equation, the total momentum of the system right before the collision is going to match the total momentum of the system right after the collision. Not 1 hour later, not 20 minutes later, but right before and right after the collision. So if you look at those two time points in the evolution of the system, one right before whatever collision happened, right after the collision, then you can apply conservation of momentum. The system to which you're going to apply the momentum conservation is the system of the things that collided, made of all the objects that collided are part of your system. So there was a collision between M1 and M2, that is your system. And when we write P total, we mean the total momentum of the system. That's the momentum of 1 plus the momentum of 2, M1 and M2. So at the initial moment, the momentum is just the momentum of the ball. So the ball has a mass M1, has an initial velocity VI, and the mass number 2 is not moving, so it has a momentum of 0. That's our total initial momentum. We're going to make that equal to the momentum right after the collision when the block putty system is moving with some velocity v. Clearly the system has a combined mass of m1 plus m2. So we set up this equation. We have all the information that we have to be able to solve for the velocity right after the collision. Dividing by m1 plus m2, we get that. And replacing the numbers, you get 2 meters per second is the velocity of the block putty right after the collision. Okay, so that answers this question. Got another question here, which is, what is the maximum distance that the spring gets compressed? So as you know, the block putty thing is moving with 2 meters per second to the right, so that means that the spring is going to get compressed, and as the spring is getting compressed, the mass is going to be slowing down. And when the mass momentarily stops, that's going to be the maximum compression of the spring. So we're looking for that distance that the spring got compressed between its equilibrium position or original length and the maximum compression length. So that's distance. We're looking for that distance. So this is what the block putty spring system looks like right after the collision. And this is what it looks like at the moment when the instantaneous velocity of the block putty is 0, which is the moment when the spring is maximally compressed. So the distance that we're talking about is that delta S in the picture, how much the spring has been compressed by the mass. So there is no friction in this problem. They said it was a frictionless table, so we're going to be able to use conservation of mechanical energy to solve this question. So conservation of mechanical energy says the mechanical energy at the initial moment equals the mechanical energy at the final moment. At the initial moment, we have just kinetic energy because the spring is not compressed yet, no elastic potential energy. So just kinetic, and the combined mass is 0.7 kilograms and the velocity is 2 meters per second, as we found in part A. So 1/2 of 0.7 times 2 squared is the initial energy. That should match the energy at the final moment. The kinetic energy is gone at this moment because the block putty has momentarily stopped, and all the energy must be in the form of elastic potential energy, 1/2 of k delta S squared. So we're solving in this equation for delta S. We know that k is 75. So plugging in the numbers and solving for delta S. Delta S would be 0.7 divided by 75 times 2 squared, square root of that, and that gives you 0.193 meters, or 19.3 centimeters. There is a second way to solve this question, which is using the fact that after the collision is over, we're dealing with simple harmonic motion. And in simple harmonic motion, the maximum speed that the object attached to the spring will have is when the object is going through its equilibrium position. So that tells us that the maximum speed that this block putty attached to the spring system will have is 2 meters per second. We already know what's the maximum speed that this oscillating system is going to have. Every time that mass goes through the equilibrium, either going to the right or to the left, it would have a speed of 2 meters per second. So there is a connection between the maximum speed in a harmonic oscillator and the angular frequency of the oscillator and the amplitude of the motion. If you remember, the angular frequency times the amplitude is equal to the maximum speed. So the angular frequency of a harmonic oscillator is given by the square root of k divided by m. When we're talking about a spring mass system, is the square root of k over m. So we have k, we have m. So the angular frequency is the square root of 75k divided by 0.7 kilograms, which is the mass. Square root of that gives you 10.35 radians per second. So the system has an angular frequency of 10.35. We're solving for A because the maximum displacement from equilibrium of this system is the same as the maximum distance that the spring got compressed, the delta S that we were solving from before. So the amplitude is the same as delta S in this problem. So the amplitude, solving for the amplitude, is the maximum speed, 2 meters per second, divided by omega. So 2 divided by 10.35 will give you the same answer, of course, 0.193 meters for the amplitude of the oscillation. All right? And we have a third question here, which is the period of the resulting oscillations. What is the period of the resulting oscillations? So this one's easier than the previous ones. It's just applying a formula for harmonic oscillator. So we know that the block putty system is going to be doing harmonic oscillations about the equilibrium position. And those oscillations have an angular frequency omega of square root of k over m. And we had already found how much was the omega, 10.35 radians per second. But we're looking for the period. But if you know omega, you know the period, because they're simply related by period is 2 pi divided by omega. So that gives you 0.607 seconds for the period of these oscillations. All right, that's it.